more about task scheduling. We didn't get to actually switching context in the last one. So, when does that happen? Why don't we just schedule or change the tasks when we set the flag? Aren't we ready to do it? Here's the problem is the interrupt code takes time, and it takes time to return from that interrupt. So while we're running that code, things can change. Maybe when the flag is set, and by the time we actually ready to switch tasks, it has to be ignored or changed. So here's the routine that I think I can pull out of the code, and I think we can maybe agree on it based on proof that I can do when I come up with the walkthrough code and do some stuff that way. Trying to keep the pace of this video moving so you don't fall asleep. Anyway, if you're not asleep yet, just wait. I'll give you something to sleep to. Anyway, let me get started here with my little book that I use as my Bible for software. It's little thoughts and weird stuff that I come up with and jot down. One of the things that we do is we mess with this thread info byte that has all these different flags in it. One of them being the TIF need resched. And another one we do is we have this thing called a work mask that goes over those bits. The details aren't really important now. But anyway, we jump to an I return to user or kernel symbol. That's IRET to user or kernel. And we end up somehow in this function called common interrupt return, which is down deep into the bowels of assembly code. And once we get to there, we restore registers as if we're preparing to return to the previous tasks. So the previous task had some stuff that we needed to save, or it would get lost when it resumed operation of its own operation, either a user task or a kernel task. User task being applications, kernel task being internals that have to get going. And what happens next? Well, we restore the registers and to return and check to see if reschedule is needed. Now, we know that reschedule is needed. How do we know that? Well, I forced the issue in the last one where we were trying to set the thing up. And then we check to see, we call schedule to perform a context switch. So that's really good. We want to look at that schedule function, which calls __ schedule, which then calls the context switch function, and then we actually switch from one task thread to the other. But here's what I found was hard to find, is that it appears that it's down in the assembly level. So if we try to look for a function that says get task flag or do something about task flag, I don't think we're going to find it. We have to get down into the test bit type stuff. Now, let's see, is there anything else I want to do? Okay, we check the flags again. If no work pending, resume the new task. If there is work pending, then we have to stay with the old one. Okay, then we'll have to talk about what this context is, the context switch. So, you kind of get the idea of that? Let's see, let me quick review it. So we set the flag, then we start to return. We're not scheduling yet because we have to get all this stuff done. To get back even to the current task, we have to get a bunch of stuff done, which during that time, it's short, but some other things could happen. We could change our mind. And so when we get there, we switch the context if it's necessary. And let's look at the code now, because all I'm doing is just rambling. I'm going to start with the vectors, and that's because a hardware event causes something to happen during execution of the program. Otherwise, it'll just carry on all by itself and we'll never do a multitask. So let's first look at the local timer interrupt. That's the scheduling mechanism that goes on, and its hex number happens to be EC. Now, we also define first system vector as local timer vector to make this calculation for number of external vectors, if that's interesting to anybody. Anyway, the first system vector happens to be the local timer vector, and that vector is subtract from that the 2, 0, and that gives you the number of external vectors. Now, why do we want to know that? Well, we want to know that so that we can make sense of the following information from the interrupt descriptor table C file, which is right here, idt.c, and we'll look down here for the timer vector. There's the timer vector, and it has associated with it a function that runs when we hit that timer event every whatever the period is. Sometimes, usually it's like every 1 millisecond if we've got a really fast system. So anyway, there's the function that gets called. Now, to make sense of this next part, these are the low levels that weren't covered earlier. And here we go down here. It says IQR entry text start. So this is the coding that goes in there for the IRQ entries. And how many entries do we have? Well, we have a whole bunch of them. And here's how they're described. Every entry has a 0x6a, which pushes a byte onto the stack, and that byte is going to be the vector that we're interested in. So every one of these vectors that's in this list, and notice it repeats this pattern for the number of external vectors. So that's why we needed to figure all that stuff out, so we could put all those things in there, that push vector. And each one of the vectors, even though they're different types of vectors with different types of call functions, they all go to jump assembly common interrupt. Where is assembly common interrupt defined? Well, that happens to be defined in a file irq.c. And rather than ASM common interrupt, this is common interrupt without the ASM on the front. And there's some manipulations that goes on that gets us to this common interrupt versus ASM common interrupt, but that's not important. I already kind of bored the heck out of myself. So let's come down here. The key thing I want to point out first is this set IRQ registers is used twice. It's used to save registers at the beginning, perform all the operations of the interrupt, and then put them all back. Takes the old registers and restores them. So any of the operations that change the registers during the interrupt processing get put back as if we were never there. Now remember, the interrupt is not a task. The interrupt is just that. It's an interrupt service routine, and it runs independently of the tasks. It is very important and related to the tasks in that it schedules the task, or it decides whether to schedule in here. Let's go a little bit deeper here before we lose our place. Here's handle IRQ. Handle IRQ is defined down in a function a little bit later here to say handle IRQ, and because we're 64-bit, it actually calls a function that's in another file called generic handle. Let me make it green. It's always good if it's green. Let me make it green. Okay, now it's nice and green, and we can say that the architecture's call to this. Anyway, here's where we are, a more simplified version of handle IRQ. Now, what is this handle IRQ? Well, remember each vector has a different uh, setup, and this one happens to be defined by this structure called DESC, which is an interrupt IRQ, interrupt request structure called a DESC. Anyway, that points to that. So you'll get a different handle for every one of the interrupts. And that handle in this case happens to be the sysvec APIC timer interrupt. And you notice that timer interrupt comes down here and calls local APIC interrupt. So what are these things on the other end? Well, that says trace the local timer entry and trace it exit. Trace entry, so you turn the trace on and you turn the trace off after you're through. For debugging purposes, we can do that. And then notice that once again, the IRQ registers are restored. Let's find out just a little bit here. We'll go down into the local APIC timer interrupt. And the important thing that we want to get to is find out the event handler. The event handler in this case, for this particular interrupt, is something you should recognize from the last video, and that is tick handle. Let me get it greened up there. It's kind of wiggling around here. Tick handle periodic. And I've put a little snippet of tick common.c down here. Here's the tick handle periodic function. It should be pretty short, hopefully. Yeah, it's not that long. And what we have to realize is that in this tick handle periodic, we do all the stuff that we talked about in that previous video about the low-level details of the task scheduling. Well, in a way, this is even lower level, but I won't worry about getting all tied up in what's low and what isn't low level. More gibberish. Anyway, the thing that we want to do is hit this return. And notice there was nothing special that happened. We pretty much just returned. So we return to the calling function. The question is, where did the step that actually decided whether to schedule or not? And either call schedule or not call schedule and just go back. Haven't found it yet in this file. This was our function that we thought, okay, this is pretty easy. We set the timer trace on, we do our local interrupt, and then we're done. Guess what? This thing is wrapped up in a bunch of layers, and that's why rather than just a simple function definition, it has this define IDT entry sysvec. So what that forces us to do is look at what's the structure of an IDT entry sysvec with the function name sysvec APC timer interrupt. So this interrupt is still going to run, but some other things happen before that thing runs, and some other things happen after it runs that we haven't been keeping track of so far. So let me go down here and kind of point out some stuff. This gets really messy, so excuse me, but if I'm going to prove this, I have to do it this way. So here we go. IDT entry sysvec function. Now, what's inside here is all the other stuff that happens in addition to running the actual function, the function that had all that stuff we just looked at. Now, when we run the function, here's the function over here, but when we run it, we have to use this other method to call the function. So we haven't even called it yet until we come down here. So down here, there's another definition of when we call the function, we go through some other steps before we actually call the function. So we go through this layer, and then we go down a little bit farther, even more so than that, to this call IR stack condition functional or function. So let me highlight that. And then this does some more stuff. And finally, we get down to where the actual function is called. But one of the things that I notice is this function is called, but what are some of the other steps that occur? Well, we do this enter, read, copy, update, read, copy, update. So you're probably really lost right now. So that's totally understandable. Let's find out what happens outside of this call on IRQ stack conditional. So we'll kind of back stuff up a little bit. Okay, here's the key thing I want to point out. With all these wrappers that occur, there's this thing called IRQ entry exit. This is the deal. This is the magic step that actually does the scheduling. So I've gone this far. I might as well keep going. But notice that this is where the function gets written, and this is where we are exiting and doing the scheduling. So let's find out what this thing is. Let's go find out the definition of this one. Here's IRQ entry exit. Let's see what happens down here. The key thing that we want to talk about is IRQ exit to user mode. That means we're getting back to the original process that got interrupted. So I'm going to do another quick search for that one. And here's IRQ exit to user mode. We go through these types of steps. And the key thing that we want to focus on is exit to user mode and prepare. Come down here a little bit further. There's exit to user mode and prepare. And finally, we do some steps and we actually exit to user mode loop. So let's find out what that user mode loop looks like. The user mode loop looks like this. It checks, first of all, we disable the interrupt so we don't have another interrupt. But we go through here and it says if TI work and TIFF need reschedule mask, then ta-da, this is where we call the schedule function. Now, let me get it so it's highlighted in green. This is really where the scheduling occurs. And once we fall through all those other loops that we found, we finally get to the common interrupt return. So that happens before, excuse me, all that occurs. So if you can kind of keep that in your head, you can figure out why it's difficult to follow through with all this stuff. If we wanted to actually look at the schedule where we do a context switch, that's really enough for another video. All we're tracing down here is what happens when we do an interrupt request, does the interrupt service routine, and these wrapper functions that go around it eventually calls a function exit to user mode loop where we actually do the scheduling. Well, you might be a little disappointed. I didn't actually do the scheduling, but I got worn out. I figured you got worn out. So I'm going to prepare a nice, clean, fresh video that talks just about scheduling and restoring the context switch. Maybe it'll be short. Let's hope so.